Good morning, my YouTube viewers. It's Crystal here. I just wanted to do a code review for you, but before I do the code review, I just wanted to talk about a little bit on probabilities. So we're going to talk about the normal distribution, and this right here is the formula for the normal distribution if you're interested in that. And we're just going to see what Wikipedia says about the normal distribution. It says the normal distribution in statistics, a normal distribution or Gaussian distribution is a type of continuous probability distribution for a real valued random variable. The general form of its probability density function is the formula below. The parameter mu is mean or expectation of the distribution and also its median and mode, while the parameter sigma is the standard deviation. The variance of the distribution is sigma squared. A random variable with a Gaussian distribution is said to be normally distributed and is called a Gaussian deviant. Normal distributions are important in statistics and are often used in the natural and social sciences to represent real valued random variables whose distributions are not known. Their importance is partly due to the central limit theorem. It states that under some conditions, the average of many samples observations of a random variable with a finite mean and variance is itself a random variable whose distribution converges to a normal distribution as the number of samples increases. Therefore, physical quantities that are expected to be the sum of many independent processes, such as measurement errors, often have distributions that are nearly normal. Moreover, Gaussian distributions have some unique properties that are valuable in analytic studies. For instance, any linear combination of a fixed collection of normal deviates is a normal deviant. Many results and methods, such as propagation of uncertainty and least squares parameter fitting, can be derived analytically in explicit form when the relevant variables are normally distributed. A normal distribution is sometimes called a bell curve. However, many distributions are bell-shaped, such as the Cauchy, Student's T, and Logistic distributions. For other names, see name. The univariate probability distribution is generalized by vectors in the multivariate normal distribution and for matrices in the normal distribution. And so, yeah, it goes on and on and on and talks about the normal distribution, but you got the gist of it and you know where you can find it if you want to look at it. So now what we're going to do is we're going to talk about the normal distribution in Python, and I have used Google Colab to write the code. And what I did was I got the code from Elijah Apaya in R. So he has written this code in R. And here is what the code looks like in R. And what I did was I took the code that he wrote in R and I translated it to Python. So this is a code review. So the first thing that we need to do is we're going to do a binomial distribution to start out with. And we covered the binomial distribution in my most recent code review. So we're going to have to import our libraries because the difference between Python and R is a statistical program that has the statistical functions built into the language, whereas Python is a general purpose program, and so it relies on the use of libraries to do what it needs to do with regard to statistics and probability. So we're going to import NumPy as NP, that's your numerical computations. We're going to import pandas as PT because we're going to create a series. We're going to import statistics, that's your statistical computations, and we're going to import Seaborn as SNS, and that is what's we're going to make a histogram. So the first thing we're going to do is we're going to create an empty list called binomial, and then we're going to have a for loop with a range of 100,000 iterations, and n equals 1,000. So it's going to be 1,000 coin flips 100,000 times, and your probability is going to be 50%. So flip equals np.random.binomial n comma p, and then binomial dot append flip. So we're going to append all of these flips to the binomial array. And then so what we're going to do is, so I've made a mistake here. Let's do that again. So that's why it's always a good thing for me to do these code reviews. So like if I've made a mistake, hopefully I'll pick it up in the code review. So there we go. That's what it looks like. So we've done our hist plot, and that's our hist plot in Seaborn. So then we're going to use pandas to create a series, and then we're going to check the mean, which is 500, the variance, which is 251, and the standard deviation, which is 15. And now what we're going to do is we're going to create a normal distribution from the binomial distribution. So normal equals np.random.normal, log equals np.mean binomial, scale equals np.stt binomial, and size equals 100,000. And then we're going to make a plot of that using Seaborn. So you can see it's very close to the binomial distribution that we have just created. And so now what we're going to do is we're going to compare the two plots. So you can see one of them is the binomial and one of them is the normal. So it's hard for me. Let me just see if I can say, let's see what happens when we do this. Try it again. Okay, so your binomial is red and your normal is blue. So now you can see the difference between the binomial and normal. So that's it for the normal distribution. We just wanted to compare the binomial to the normal, which is interesting because for the normal, you had your highest rate was 2,500, but when we compare the two plots, for the normal, the highest rate is, 1,000. And for the binomial, the highest rate is 2,500. And when we compare it, it's 2,500. So that's a bit unusual, definitely unusual. But that's just the way it looks when you compare it. But whenever we do it individually, they look the same. Let me just see. So that's how it looks. That's what it looks like, and I can't do anything about that. So I'm going to go ahead and conclude this presentation because we have talked about the normal distribution. We did a binomial distribution and we did a normal distribution under the same parameters, I believe. Let's see what it says. Yeah, because the normal distribution is based on the binomial distribution. And so since the normal distribution is based on the binomial distribution, it is based on the same parameters. And there we go. If I made a mistake in any of this, please let me know, but I'm just using the code that I found on the internet to do it. And so, because here, this is the thing that concerns me a little bit. It says data equals normal, bins equals int, np seal, np dot square root, normal dot size, label equals normal. So, but we're using the same code that we used for the binomial that we've used for the normal. So I'm not sure exactly what the problem is, but if somebody watches my video and they want to tell me what I have done wrong, then certainly I'm open to suggestions. So thank you very much for watching my video. If you like my video, please like, subscribe, and share. Thank you to all my subscribers for supporting my channel, and I look forward to making more code reviews for you in the future.